I don't have a appropriate title, but that is the one here. We given the orbital element, then we're going to find R and V. Basically, this is the reverse process to what we have learned before. So here, if you like, we can give a title, say, determine R and V in the perifocal coordinate system. Okay, what is the perifocal coordinate systems? And that is the one. So say if this is our orbit, this is our focus. So perifocal system is P and Q, and perifocal system is PQW. Okay. So W, using your right-hand rule, W simply is out of plane like this. That's what we call the perifocal system. Okay, so right now you have to gradually adopt the terminologies for communication. So basically here we going to describe the RV into PQW. Okay, so which means, let me emphasize, is into PQW. If you remember, I just erased here, yes, and you can see we give the RV into the IJK coordinate system, and some are a little bit different. So sometimes we need certain, down the road, we need certain kind of the transformation of the coordinate systems. Okay, that'll be necessary. But here, for this one, let us focus on this one. So from here, I want to come up with the two formulas. That is, those are given in our textbook, and those formulas could be very handy. So here I give it to you right away. So from here you can see from our equation of the orbit, we have P1 plus E cosine nu. And let me give you those kind of notations. So for example, here we, at this moment, the object is here. So this is R, okay? And this is nu. So here, for given the orbital element, so that means including nu, right? So nu should be a given numbers. So we have this one. You can see. So R, this is the R vectors. Then that R vector can be very straightforward, and that one simply is R cosine nu in P. Let me say this is the unit vectors, okay? And this one is the unit vectors. And plus R times sine nu Q. Okay, so that one we done this one. So PQW equal to this one. Okay, so these equations appeared in the textbook. In our textbook, you can find it. And then we're going to determine V. V in PQW. Basically, here the starting point is we maybe back a little bit. So here we given nu, we given P, and we know the E. So here P, E, nu are given, so we can calculate R. Should be no problem. So here is everything here in this equation is known. Okay. So now we calculate this one. For this one, there's a really nothing so straightforward. So in practice, we simply starting from simply take the derivative with respect to time of R PQW. We see what happens. Okay. So for this one, simply we have these parametric expressions. So that one we've done is this. I simply take the time derivative with respect to time on individual terms. And so from here, you should expect R and nu are time dependent. Okay, so here, if you put in here, so in this way I would say mu r time dependent. So that means we have to take the derivative on those kind of terms. So here will be equal to, let me do this one quickly, r dot cosine nu minus r nu dot sine p. So this one is the time derivative of the first term. Okay, and then I proceed to the next term here. So that is r dot sine nu plus r nu dot cosine nu q. Okay. So from here we need to determine. So later I will give a scratch calculation, but let me list the results first. Okay, so we can calculate, we can determine r dot equal to mu over p e sine nu and nu dot later I will give you a quick derivation about the two terms, but here we just take them. Okay. So therefore r, the v, we can rewrite this one can be equal to mu over p minus sine mu p plus e plus cosine p. So there's a PQW. So this is a little sections and particularly described by this. For me, I won't be able to keep this in mind forever, okay? And today I know, and then tomorrow I will forget it. Okay, so I would say the two information will be on the cheat sheet. And regarding the R dot, and so here I'm going to show you R dot equal to how much, okay? So R dot is simply we take the derivative from our orbital equations, 1 plus e cosine nu. Okay, we simply do it, and from here they have a few steps. I don't think that is so critical. And in these informations and a few steps later on, then you should be able to get this one, mu over p times e sine nu. And in those steps, you must have used the h equal to r squared times mu dot. Okay? So I believe this derivation should be available in our textbook. It's not that critical, so let me skip. And for determining the second term, and that will start with this. If you remember, we have h, our the magnitude of our angular momentum is r squared times dot v. Okay, that is from our chapter 1. So starting from here is h divided by r. Okay. So again, here we plug in, and h r equal to p Okay, so again, I use the equation of the orbit and for r, and then we simply implement this one. Then eventually you will get is mu over p and 1 plus e cosine nu. Okay, and here have one step simplification, you get this one quickly. Okay, so the derivation is not important, but here the box's information will be useful. Let me see if there's an example here. Here has a very simple example we can try. Okay, so here we given the P equal to 2.25 and du, and E equal to 0.5, and mu 0 equal to 0 degrees, then we want to determine R. So R from this calculation, P 1 plus E cosine mu 0. We plug in the information is 2.25 and 1 plus 0.5. So that is 1.5 du. Okay. So with this one, so therefore R PQW, we simply plug in the informations, and that will be equal to 1.500 in PQW Portland systems. And for V, again, simply plug in that equation directly, so that will be 0, 1, 0, and PQW DUTU. So this one is a very, very straightforward substitutions into the formula. Okay. So I think that is for these sections.